Okay, sweet. So we are ready to go. So we are back with the self-study for calculus. I think we will start with our Anki cards. I do want to spend some time thinking about as we bring this. Well, I still have a few things to learn, but as we come up on closing, I want to think about the process by which I learned calculus, and then what things would be better or would enable me to have learned it more quickly. So, yeah. Okay, so I guess we'll just hop in. I guess I do want to mention one thing before we go forward. And this is about the hiddenness of learning. So, often in learning, we'll find a strategy that will enable us to learn a particular thing. And then we don't ever, look in retrospect at our strategies that we use to see if we can improve. We never look for efficiency things. We just sort of pick or find the, school strategy that works for us and then use that. And the issue is that the first strategy we happen across is most certainly suboptimal. So we'll grab a strategy and continue to use it, right? Despite the fact that there are greater strategies that could be used. So I guess it's important to take time to think about what it is you're learning, and after you've learned it, and think about what things could have gone better, and what things didn't go so well, to really determine what was most efficient. And also, in part of that is doing experiments to see if something was good or if something is good. Because if you're always doing the same process, you can't know if there is a better thing that you could be doing. So it's only through experimenting that we can reach that. Okay, perfect. So we'll begin to review. I did find that I had added some calculus cards to my default deck, and so we do have more than usual today in the new category. Okay, how do you find local extrema? Okay. So for this one, you take the tangent line where it's 0, and then you take the second derivative at that point. And then if it is greater than 1, then it is, or greater than 0, then it is a local minima. And if it's greater than, or if it's less than 0, then it's a local maxima. Let's see. So these are the critical points, yep. And then we use the second derivative test. If the function is greater than 0, it's the local minimum. And if it's less than 0, that's the local maximum. I still don't understand. So we're going to dive in just a little bit here. I still don't understand why it is the case that that's true. Could you describe why it's the case that when finding local extrema in calculus, that if for the second derivative test, if the result of the function is greater than 0, then it's the local minimum. And if it's less than 0, it's the local maximum. I'm not sure if I follow why that's the case. Intuitively, I would think that... Yeah, actually, I'm not sure. Could you describe? Okay. About the curvature or concavity... Okay. Wow, you didn't. Okay. Okay. Now, if you're at a critical point where the first derivative is 0, yeah, okay, I understand that. That the that we're changing from a negative to a positive. Oh, the second derivative. So this is something I didn't grasp earlier. The second derivative tells us about the curvature or concavity of a function. Huh. Interesting. Could you describe why the second derivative tells us about the curvature or concavity of a function? Question mark. Presently, my understanding of the second derivative is that it is the rate of change of the rate of change. So I don't have a conception for how it expresses as the shape of a function. Question mark. Oh. I'm sure this has to relate with the fact that we're deliberately choosing critical points, which are either a local minima or local maxima. So, yeah. Okay, so when I was talking about, let's see, this earlier, I think I was onto something here. Oops. So what I was describing is that we are at a critical point here, and I guess the second derivative tells us what's going to be occurring right at the critical point. So if we're increasing, it's a positive, which means we're at a local minimum, right? Because if we increase, that means we're at a low point. But if we decrease, that means we're at a high point. And so I guess the resulting action would be for that. So I think I have a deep understanding of that now. So I think we can go ahead and continue. I'm going to zoom in a little bit here. Okay, what are the concepts of the right-hand to left-hand limits of calculus? So right-hand to left-hand, this is the idea that we can find limits as they're approaching from the left side and from the right side. This is the branch of mathematics that deals with limits, infinities, and derivatives, integrals. It helps us understand rates of change and continuity. Yep. What makes a discontinuity non-removable? This is when the discontinuity, we'll give an example, that the denominator results in 0 at some point, meaning that the output is undefined. And it's non-removable because we can't factor it out such that it no longer is 0. So we don't have, another way to put it is that we don't have an algebraically equivalent function that does not have the discontinuity. A discontinuity is non-removable if the left and right hand limits at x equals a are not equal. Okay, that was not what I thought it was. Huh. So let's ask this question again. because I was not expecting that. And I'd like to try to, oh man. I'd like to try to get through these quickly, so I might just speed through. But I also want to ensure that I'm okay. Yeah, so I was correct, but I wasn't this is an example that I wasn't sure of. So I think we'll just grab this definition. It express areas under the curve as limits of Riemann sums. So I understand the conceptual behind that. I don't know the exact expression yet. I'll be focusing more on that when I go over Riemann sums. Break and jump and hold as continuity. I don't know if there is a difference. Holes can be removed, jumps cannot. Okay. The derivative operator is dx over x, or d over dx. Okay, slope of the tangent line relates, or I guess slope relates to the derivative because we're looking at the slope of the tangent line, and integrals are about the area under the curve. In calculus, how do you integrate using Riemann sums? So you take rectangles under the curve, or so you approximate the area under the curve through rectangles, and as the number of rectangles you have approaches infinity, you'll have an equivalent. You'll understand what's under the curve. Okay. A function returns a value. Expressions do not, or has an input-output relationship. That's another way of putting it. Yeah. Oh, what's a limit within calculus? A limit within calculus is a description of what a function does as it approaches a particular number in terms of input and output. This concept in calculus describes the value of a function. Okay, this is a limit. Okay, so this is the derivative here because we're looking at the slope. So this is the delta of y and the delta of x, and rise over run is that equation there, and x and y like multiply together to equal our area. So that's integrals. Oh, is that correct? Yeah, yep. How do you find inflection points on a function? So when the slope, the second order slope goes negative or positive when it passes 0. Okay, perfect. The reverse chain rule, I'm not a clue. Okay, I need to mark that down. I think we have it down here somewhere. So I'm actually going to bury this until tomorrow. Bury a card. Hotkey. The minus key to bury a card. Minus. Card buried. Okay. And what burying does is it just pushes it till tomorrow. With the summation operator, it looks like an E. Sigma. Yep. Use substitution, not a clue. Euler's number, it's like 2.41 something. And this is a number that's often used for decreasing or increasing natural progression, or natural functions, you could call them. And it's derived by 1 plus 1 over n to the n. 2.7. Okay. Okay, don't know this one, so we'll push that one out. How are limits expressed syntactically in the context of the integral symbol? So the integral. So it should be lim to, with an arrow to the limit. Okay, so, oh, if we're doing the integral, then it's upper and lower limits. Okay, that makes sense. Composite function. This is a function within a function, I believe. Yes. It's a function made by applying one function to the results of another. Okay, so it is a function within a function. Yeah, I think that's close enough. Linearization is when you approximate the function using the tangent line. Find a limit. You could do substitution. So we substitute the limit in the equation to see if it results in a number. If it doesn't, we can find an algebraically equivalent function and see with the hopes of making or getting that output. And then there are a couple other rules that I'm not familiar with, like L'Hopital's. So yeah, I have to do some work on L'Hopital's and indeterminate forms, rationalizing for limits. Okay, so that's good enough. It's the S. Rationalizing involves multiplying by a conjugate to limit square roots. This simplifies the expression, often removing indeterminate forms. Okay, so in addition to factoring out expression or a function, or factoring out portions of the function to find a mathematic or algebraically equivalent function, you can also instead of factoring, you can also multiply such that you can rid yourself of the sort of nasty portions of the function. So we actually have that one down. Okay, and then a derivative in calculus. This is the slope of the tangent line. It gives us the slope for a given area. Jump discontinuity. This is one where an output is undefined or for a given input. Sudden jump. Okay, yep. L'Hopital's rule. First, confirm the limit gives 0 over 0 or infinity over infinity. Then differentiate the numerator and the denominator separately. Take the limit of the new fraction. Repeat until the limit exists. Okay, so that's reasonable. I will send it through again just so I remember it. This concept is counted as a measure of how the function changes as its input changes. It represents the function's rate of change. This is a derivative. The use of the squeeze theorem. I don't think I know this one. When a function is difficult to evaluate directly, if the function is squeezed between two others that share the same limit at a point, then it also must approach that limit. It's useful or tricky for oscillating functions. Okay. Okay, I think this is the Weed applies this squeeze theorem to like this guy here. So yeah. So if this one and this one both approach the same limit, then okay, actually I do need a little bit more for the squeeze theorem. I think I'm going to bury this one. Okay, squeeze theorem. Derivative operator. Squeeze theorem. I swear I just talked. Oh, what's the use of it? Okay. Okay, so I had that. So we'll actually send that through. What's the power rule for derivatives? Okay, so this is very important. One should not forget this. This is how you take a derivative. Okay, so I will decrease the power of the function, and then at that given level I'll multiply. So let's see, x to the n equals n times x to the n minus 1. Perfect. Okay, makes derivatives super quick. What does it mean for a function to be less than equal to another function? Is the outputs always are less than or equal to? if every input in a certain interval, the output is always less. Oh, okay. So it's about the relationship of the inputs and the outputs. So if for my input, so if I had a function where f of x is x minus 1, and then f of x is x, that means that f of x minus 1 would always be less than or equal to f of x equals x, because the output for a given input, the output will always be less than. Okay, reasonable. The difference between an infinite discontinuity and jump discontinuity, this is when the positive and negative approaches, or let's see, the left and right approaches to the limits results in infinities, and as it approaches the limit, which creates a discontinuity. And then a jump discontinuity is one where it does not have an infinity, so it's just like undefined at a given point. A whole discontinuity can be filled, meaning that you can factor it out, or find the conjugates. I think that's the word they use anyway, to make a algebraically equivalent expression, either by multiplying the function with like upper and lower, or like by 1, or by factoring out to remove the discontinuity, to remove the discontinuity. Derivative operator is dx over d over dx. Why? Okay, I'm getting that one wrong. So x is on the, we'll just remember that x is on the bottom, because for the slope, which we're finding for the derivative, it is y over x, right? Or delta y over delta x. And so I think that is reasonable, and I think we'll remember from now on. How are limits expressed syntactically in the context of the integral symbol? Upper limit is on the top right of the S, and the lower limit is on the bottom right of the S. Boom, boom. Perfect. Euler's number is 2.7 something, and it's for rapidly growing and decaying functions. That's yeah. Okay, rationalizing. Rationalizing is, okay, so I understand why it's called why we're rationalizing now, because when you have square roots, sometimes they result in an irrational number. So I think the square root of 2 is irrational. Actually, I'm almost certain it's the case. What is the square root of 2? Of 2. Is the square root of 2 irrational? Yes, it's an irrational number. So we're rationalizing it by multiplying, like if I had square root of 2x, yeah, if I had like this, this is my best understanding presently, but if I had the square root of like, oh heavens me, okay, if I had like the square root of 2x over, maybe over x. All right, well, we'll have to walk through some, because I don't know if it's over everything here. Anyway, the process of rationalizing is bringing from an irrational, which is often caused by having a square root something, right? By multiplying it out by its conjugate. So, conjugate by eliminating square roots. Perfect. Simplifies the expression, often removing indeterminate forms like 0 over 0. Multiply denominator and numerator by the conjugate. So I'd like to know what what a conjugate is in mathematics. What is a conjugate? Is a binomial formed by changing the sign between two terms? For example, the conjugate. Okay, yeah, that's good to know. So we will easy that. L'Hopital's rule says that if we have like a really hairy if we're finding finding the limit is really hairy, you can take the derivative of the top of the fraction, or sorry, if we're finding a limit is hairy for the top and bottom of a fraction, we can take the limit of, or sorry, not the limit, the derivative of each, and then try to find the limit there. Okay, we have to confirm first that it's 0, 0, or infinity over infinity. Differentiate the numerator and denominator separately. Take the limit of the new fraction. Repeat if needed until the limit exists. Perfect. I'm gonna send that through one more time. This means that for a given input, the function's output will be less than. L'Hopital's rule says that if you have a function that results in 0 over 0 or infinity over infinity, then you can differentiate the numerator and the denominator separately and then find the limit. If it's still awful, just continue to differentiate until it works to find the limit. Okay, perfect. I finished it. Now we're going to grab the conjugate here. What that is, what is a conjugate? And I think this is a math broadly kind of thing. Probably an algebra. Algebra. Okay, and then we'll just send this guy through. And then we will add a reverse. Perfect. Okay. So one thing that is important about, a learning activity is finding what your criteria are for finishing. I feel like I was very not clear about that. It was sort of a figuring out of what I wanted my criteria to be as I went through. And so I'd like to maybe spend just a little time fully determining that. Okay, so then we'll bring this guy here, Dex, sync, browse. Actually, it'll probably be an add here. Okay. Okay, so I think if we want to attack, or it might be useful to merely attack the MIT final exam and then go from there. So I did pull out everything that, So I do have this procedure list where we could go through each one. Well, let's see. Okay, I think I'm going to do a quick pass through the procedures list. Identify everything that I am I don't have an idea for. And then after that, we'll see if we can solve each of the MIT questions. And then obviously, walking through the MIT questions, knowing, or if I were to go through the MIT questions, and then like go to a computer to determine, or I guess go to the computer I'm using to determine what the answer is, if I'm able to find it myself. Obviously, in some ways, it's not a real test because I'm like working through the problems rather than having like my understanding stand on its own. Though I think we'll probably do that, and then we'll select a few random problems from somewhere. And if I can solve those, then I think we'll call it there for calculus. Obviously, there is a sense in which I have in terms of what is typically done for calculus, for teaching, I have very, very, very little practical experience of doing calculus, and have a much greater conceptual understanding for calculus, which honestly I'm more interested in. But so that is a reality for me. One thing that Anki actually does poorly, that I think which I'm going to be addressing with this application I'm building, is that Anki, like, there's no ability to do exercises with an Anki. You could hypothetically put some exercises in, but because of the nature of Anki, for those exercises, you're more likely to remember the answer rather than to know the process by which your answer is derived. And so, and the key in being able to memorize the process is to be explicit about something being an exercise, and then for a given exercise, vary along the variable parts for that exercise, such that the core exercise is the same, but you can't memorize the answer. So this could mean, like, for a given set of exercises, we'll say you're learning like predicate logic. For a given set of exercises that are attempting to teach you what the difference between a modus ponens and a modus tollens is, that would be one exercise, and each of those varying instances of the exercise would be given at random for that thing. And then additionally, that exercise would exist as something akin to an Anki card, such that the spaced repetition nature of that exercise for that unit that also has all those exercises in it, such that the procedure you use to arrive at the answer is the thing that you memorize, rather than the concept or the answer, or memorizing the answer itself. And so by nature of the weaknesses of Anki, well, obviously it's not reasonable to blame this entirely on Anki. Like, it's merely a tool, but it certainly doesn't help me in the ways that I would like for learning mathematics, right? For this thing. So yeah. Okay, let's see. So I think I'd like to, okay, so I think we're gonna go through this procedure list. I also want to know how to factor more. Like, if I receive a complex function, I just kind of have to figure out, kind of reason, oh, it has to be this or this, and it's hard, I can't factor it out. So I want to make sure I have that procedure down. So factoring out polynomial expressions, or functions rather, because presently I really don't have that down, and I want to make sure I have that down. I only can sort of remember how that's done, and maybe there isn't a good. I'm almost certain there's probably a good procedure for that. Okay, so we'll go through. Okay. So I'm actually going to start deleting these for ones that we have. Okay. So discontinuities and asymptotes. Okay, I think I'd like to understand the ranges and domains for functions. I know first order and second order if I know how to get local extrema, sketch graph and label extrema, inflection points and asymptotes. I know how to do that. Linearization, easy. How to use a linear approximation for a function. I don't think there's much there. I need to learn how to integrate using Riemann sums. Taking a definite integral, don't really have an issue there. Though I'd need to like have something there with the power. Or no, actually, I think I could reasonably do the power rule. Okay, understanding how Riemann sum estimates relate to the actual amounts for a definite integral. I think I'm actually fine there. Though I do want to capture like the left hand and right hand Riemann sum things. And then I think I'll delete this and delete that. So I really only have 4 here. And then I'm going to do a quick one over to make sure. And then I thought these were for limits. These rules here, I thought they were for limits. So I actually think I might have to do a little bit more here. Because it's saying we're differentiating using the rules. And the only one I know how to differentiate using is the power rule. So actually, I might have to do a little bit more there. Okay, I'm going to go to the bathroom real quick and I'll be back. Okay, sweet. So, mm-hmm. Let's see. So we are about like 10 minutes out. I would like having to have more time to push through. It seems like a lot of the time is taken on going through the Anki stuff and reviewing that. That is good. I think we'll probably end there and then start book up next time. I might expand the time that I stream for such that it's reasonable that I could get through more material, because it seems like the last few hours have mostly been in review. I guess especially for Mondays that's the case, because Mondays are when I have the rest of the things. Yeah, so I think yeah, I think we'll shoot for that. So what I'm going to do next is we're going to go through all the Calculus 1 procedures list, make sure that we understand conceptually and have like a couple experiences there. And then we're going to go through the calculus test, solve every problem, and then hopefully find a different test and see how well we do on that. If we get a passing grade, then I think we've completed it. So I'm going to shoot for 3 more hours in total. I'd like to be under we'll just say I'd like to be under 16 hours. Oh, so I guess that'd be 17 hours. Though I guess the last few have been 30 minutes, so we're not exactly each day is 1 hour anymore, so there's that. But yeah, I think generally we'll be shooting for that. Sweet. Awesome. Well, I will see you guys tomorrow then.